I look at the level and the support. I'm not sure if the publishing with the or the out was on and after the week of the one just start learning because they have the different study because there's also the dynamic but there's also the cloud like
Yeah, but we will do that on level, but they can send somebody in and visualize what goes the survey.
it's not treating them only the department because you know, we did not make heavily before us and let them for the reason I did this.
And the thing in disclosure, we're running it on a virtual.
Yeah,
It's
it's
not
not
a
a very important topic. There's one that's dedicated CPU, so it's not a machine but
No.
electronic that's in the
There'll probably be some, let's say, there'll be probably some duplication on their end.
Yeah.
To run work on there. For some, one machine failed, we will note it, this is not looking.
and I think there is some other risk that
Like that's not a problem, probably understand how quickly you can recover from it.
that is something to be this. Like you like right now, how long will it take? And more or less good timing.
No, but they say it's hours and it's
Yeah.
fine, yeah, and that's fine, but the thing is, you need to have a backup. I'm not saying, like, we need to have a backup on that same machine, you need to be able to recover quickly against it. But we also need to export that into a safe location.
Yeah, that is what yeah, descripted does it weekly, at box one. Then daily does also actually could delete the but they become yeah, that happened. But we can
Yeah, the machine goes in explosion. Yeah.
that's exactly starting and what it's yeah, should see is why seven like that now take this like so to the next machine. For the tech getting better. And we can check because we can also move the to start on a current. You or you are
Um, we can actually do some discharge because they have now the full storage,
achievement. You should certainly review.
How does it look? Hi Tor, good afternoon, welcome. We'll start at 4. You're very welcome. We are expecting quite a few more people. Not too many, but at least a few more. So in this case, I'm gonna wait at least 1 more minute. Je zit er nog niet in, toch? Aitor also give us 1 or 2 more minutes. Well, we kick off. Because in total we had 15 registrations. So usually 30% no show is realistic, but I would expect at least be 8-9 people to join. Yeah. So I guess people are in back-to-back meetings. Oh yes. Good afternoon, Gennaro, Maria, Aitor. So let's start the third uptake dialogue, and today we have I do think, very interesting topic, well, like the previous ones, but this is all about the past, present, and future of software quality assurance, and the core presentation will be done by Peter from Front-End Art, and he is the research team lead. And in a few minutes, he will share all the details, and their vision, and how the technology works in this case. But before we go there, a quick overview of what we're going to do. So I will share, let's say, 1 minute of background on the uptake dialogues, and also give the floor if there are any updates, because for the uptake project, and I guess most of us is part of the project, so we will meet each other also in Cagliari in next week, but would be good occasion if there is some update. And then we move on to the presentation by Peter, and then obviously time for question and answers, and then we move to the closing remarks and announcement of the next dialogue. One of the important things, I think, for the uptake project, we're trying to complete the so-called DevSecOps cycle. We have been working on this to get it complete and to identify all the positions of the different partners in the DevSecOps cycle that we see on the right side of the slide. And today's presentation by Front-End Art is a lot about the build phase of software and managing your risks during the build phase, which is building some software, I think, is easy. That kind of everybody can do it, especially with some help by AI. But do it in a secure way, do it in a responsible way, and also do it in a future-proof approach is getting closer to an art. And I think that is also the reason why the company is called Front-End Art. But we will hear more about that. A little bit of background on the dialogues. This is a great way how we can share high quality content and share some thought leadership. I think today we have both high quality on the quality assurance, as well as vision on how to deal with software development. This can close some knowledge gaps. It helps us to better understand the relevance of new products, of new latest developments, It's a good way to engage with our community. So we have in the EPTech project quite a good community, although, and that's fully blaming on my side, we have been a little bit silent on the EPTech dialogues for a few months, but I think we all had a really busy run to the end of the year. So with fresh energy, we started this year with setting up a new series of dialogues. And it's also a great way to put relevant outcomes and developments in the spotlight and to engage with guys, colleagues who are not part of the EPTech project. So we continue on this, and I would like to ask if there is any update, comment we would like to share or to make at the moment. Please use the chat if you want to ask something. Also for the presentation itself, if there is a clarification because of a certain term that is not that well known, or please drop your question. Is it more a discussion-oriented question, or better to have the discussion at the end of the presentation? So, but feel free to engage and to ask any question you have or share any idea through the chat. And then I would like, if there is no addition or question, move on to the presentation by Peter. So Peter, feel free to take over the screen, and the floor is yours.
Thank you, Mark. Thank you very much. Okay, you should see the slide I'm showing. So great. Thank you very much for invitation to this EPTech Dialogues. I'm very excited to be part of this great series of events. My name is Peter, as Mark already introduced me. And the presentation I'm going to give you has the title Past, Present, and Future of Software Quality Assurance. So let's dive into it. And as Mark said, if you have any clarification questions, interested in any details, feel free to interact. It's not a university lecture, it's more like a dialogue, as the event title suggests. Okay, first of all, let me introduce my company and myself, just to highlight what entitles me to speak about this topic today. So I'm here to represent a small medium enterprise in Hungary called Frontend Art, which takes part in the EPTech project, but also many other EU projects as well. And it's specialized in offering various quality assurance products and services, among many different things, but one of the strongest legs of the company is providing quality assurance products and services. But we work and offer customized software and AI ML-based solutions to customers. The origins of the company is stemming from an academic environment. The company was established in 2001 as a spin-off company of the local university, operating in the same town as the company, where actually a handful of researchers worked together with the Nokia company, which was a leading mobile manufacturer at that time, owning the leading mobile operating system called Symbian at that time, who wanted a deep analysis, code analysis for their software to detect certain performance and functional problems in their code. And actually, this is the product that was developed back then. And actually, the company was brought to life to commercialize and build on the research results of the university. This is how it started, and since then, Frontend Art grew a bit, and it today offers a series of products and services, as I mentioned. The most relevant one in the light of this topic is a static source code analyzer. So we own a full a custom developed toolchain called Source Meter. We also have a product called Test Navigator that offers test management and test coverage measurement for quality assurance teams. We have a prototype tool called Cody, which is basically supporting the development process and helps monitoring productivity. But we also offer services, testing services to third-party companies, and also quality and security evaluation for large enterprises who would like to use some third-party components, or they have some external software vendors and want to certify the quality and security of the shipped code. Okay, and a few sentences about me. I worked for Front-End Art more than 10 years now, leading the research and development department, and basically acting as a R&D project lead in the company, because we have a lot of research activity within the company despite our small size. I graduated and got my PhD from the university here in the town in 2015, and actually I spent my years back then studying the product quality, modeling software product quality. So I think I can share some of my insights during this talk. I don't think I need to motivate too much why I talk about software quality today. So whoever is here, I'm pretty sure knows that software quality is really, really important, because there's software everywhere. So it's basically all the critical infrastructure run by software, finance, healthcare, transportation. But with the growth of IoT, basically software appears literally everywhere surrounding us, starting from TVs to air fryers, etc., etc. So there is a lot of demand for software, and as you can see, the global market growth is quite steady. So it's no question that the quality of this software is really, really important. The failures are visible, more visible than ever before. So whenever there is a major consequence of a software hiccup, it's all over the media. So it causes immediate cost troubles for the company and reputation loss, etc. So basically, we can say that quality is not a technical issue anymore. It's more at the level of a business risk itself. So handling and managing quality in the right way is not just the interest of the development team, but also the whole business operation itself. Okay, to demonstrate the cost of poor code quality, I brought you some very, very, very well-known examples. So, of course, there are millions of similar small issues, but these are extremely well represent how small and how naive problems that could have been easily spotted by a proper quality assurance process can go live and can cause really, really big problems. The production defects, of course, have some direct impact. For example, they can cause downtime, security breaches, but also, as I mentioned, the reputation damage is quite substantial as well. Studies show, and our experience also underpins, that delayed bug fixes cost at least one order of magnitude, but frequently even 2 orders of magnitude more than if they were fixed during an early phase of the software development, like during developing the system before going live. So the after release bugs cost really, really more to companies, to software development companies. Okay, the technical debt accumulates in the code base silently, which means whenever you apply, modify the source code without proper care, knowingly that the quality of the solution is not the best, but it brings you the biggest short-term return, that is basically having a debt, right? Because it accumulates in the source code, and after a while, it makes the further development of the system more and more expensive. So it's a really, really dangerous thing. Okay, and the few actual examples I brought you is the WannaCry ransomware. You must have heard of it. It was quite all over the news. And basically, a very tiny bug has been exploited. The exploit is called the Eternal Blue exploit, which attacked the Samba implementation, the Samba protocol implementation within the Windows system, which was due to a very simple type incompatibility issue. As you can see in the sample, the parameter has a double word type, and it's stored in a local variable which has single word type. So of course, with a certain payload, one can take over the control over the system, injecting some executable code, and that made it possible to build a ransomware called WannaCry, which caused around $4 billion worth of damage worldwide. The other really famous example is the Ariane 5 rocket software, which again contained a very tiny type mismatch issue that could have been easily coded by proper analysis. It was actually borrowed from the Ariane 4 software, but since after the upgrade to Ariane 5, the system changed so much that the value could not be stored in that type of variable that was enough for Ariane 4, and that caused a deadly exploitation. Okay, and it cost $370 million. Okay, so these really tiny bugs, really tiny issues, that could have been really easily spotted and fixed with changing one character in the source code, went over and got live, got released, and caused really, really big problems. Okay, that's again a really interesting phenomenon about software quality. And please excuse me from starting from that far away. That's my extensive academic background. So I like to build up all the notions from the beginning, but it's really interesting to understand the nature of software quality, because there is a concept called software erosion or software decay. Coderot, they call it many different ways, which describes how the quality of the software evolves during the lifetime of the software. Okay, and there are two curves. The upper one shows the typical failure rate of a hardware component. And as you can expect, at the beginning of the life of a hardware component and at the end of the life cycle of a hardware component, these failure rates peak high, right? Because due to some manufacturing problems at the beginning, some of the hardware components might be error prone, but after a while, if it survives this infant mortality, then basically the failure rate stays quite stable during its life cycle. Then it gets old, and of course, the failure rate goes high. What you would expect from a software is that you build a software system. Of course, at the beginning, there are some baby problems, some errors due to the implementation, and after proper testing and using the software itself, removing these bugs, the quality of the system remains stable throughout its lifetime. But that is just in an ideal world, because in reality, and what we experience as well, and it's basically supported by many other studies, is that the software quality erodes. Okay, it gets worse and worse with the time due to the frequent releases, frequent changes of the source code. So a software system is never done. So you always put in new features, release new versions of the software, And naturally, with the addition of a lot of features, the failure rate jumps high. Then you can, of course, test it and reduce the failure in the system. But overall, as you can see, this curve goes slightly up after each release. The failure rate is a little bit higher than it was before. Okay, so and that's what we experienced many times in practice during companies. The older the system is, the harder to maintain, the harder to add new features. Without conscious quality assurance activities, basically the system will reach a point where it's cheaper or more economic to rewrite from scratch than to modify or add new features. That's a very interesting and important feature of a software system you need to be aware of. Okay, but as I said, I'm coming from an academic background. So when I speak about something, I would like to define the term itself. So I'm speaking about software quality, but what software quality is? And it's already a hard and tough question. So because software quality is much, much more than just functionally correctly behaving system. So the closer we can get to a universal definition is by observing the ISO standard is 25010, which is defining the software product quality. And the standard defines several so-called quality characteristics, which impact the overall quality of a software product. Okay, and these characteristics are the maintainability, security, reliability, usability, compatibility, performance, functional suitability, and portability. Okay, these are quite high-level concepts, but they are broken down into even lower so-called sub-characteristics. For example, in the slide, you can see I break down the maintainability characteristics. The standard defines that maintainability is influenced by the modularity, reusability, analyzability, modifiability, and the testability properties of the source code itself. But that's it, all that the standard gives us. So basically, there is no precise definition how to calculate these kind of measures, right? So it's high-level conceptual descriptions of quality. So there is no method, no straightforward method how to quantify these measures. Okay, but I spent quite a lot of my PhD investigating this topic, but that's not the main topic of this talk. Why I wanted to highlight this concept is that you need to be aware that quality itself is a complex term, and it's much, much more than just having a bug-free software that functions correctly according to the specifications. So that always needs to be kept in mind when we speak about software quality. Since I promised in the title that I will speak a little bit about the past, let's have a slide on what actually quality assurance meant some 10 years back, when the world was a little bit less quickly moving and changing. Basically, software systems were developed more with a waterfall mindset rather than this iterative agile mindset that is trending today, which made this so-called B model more than suitable for quality assurance, which is basically that you first collected the requirements, designed the system, implement the system, and at the last stage, when everything was ready, then came the quality assurance in form of testing, and manual testing was dominated at that time. Also, the responsibility of quality of the system was entirely outsourced towards testers, right? So there was this developer versus testers mentality. So developers were writing the code, and testers were trying to break the code, right? And they sometimes worked against each other rather than forming a unified team. But this approach is not really feasible and suitable for today's development, today's requirements towards the system, because the testing alone cannot ensure the proper quality, especially if it comes very, very late at the end of the development life cycle. So the development is not that linear anymore. So it's more like iterative and incremental process. So basically, there is no such thing that end of the development, because we have shorter sprints in an agile fashion. So basically, quality must start earlier. Quality assurance must be an integral part of the whole software development life cycle itself. So Mark mentioned that in the Uptake project, we are trying to cover the whole DevSecOps cycle. And basically, that's true for the quality assurance and security as well, because it needs to cover all phases, of course, in different forms with different activities, but rather than having a testing session at the end of the development, it's basically a continuous activity starting from designing the system, designing the proper quality requirements, and applying certain techniques and certain methods throughout all the phases of the software development itself. So the solution is to shift everything left, basically to start quality assurance activities as early as possible during the software development life cycle. Okay, and the owners of the quality are not the testers, not the quality assurance team anymore, but more of a shared responsibility where basically developers own and are responsible for the quality to a certain level for the code they are producing. In this way, we can get faster feedback loops, so we can react and act earlier. Moreover, as I try to emphasize with this ISO standard, the aspect of quality has broadened, fortunately, and software development teams are not focusing only functional correctness anymore. So there is much more in software quality than just functional correctness. For example, security and performance, the user experience became vital and essential components of software quality, and software development companies paying more and more attention to those aspects of quality and not just the functional correctness in isolation. Moreover, if you look into more at the code level, maintainability is one of the core characteristics that also impacts the overall software quality, which will determine how easy the system will be to modify, to reuse, to test throughout its life cycle. And we know that the initial development is basically just the 20% of the whole life cycle of the system. The remaining 80% is basically maintenance and evolution, right? So it's not the same if the system is easy to change, easy to modify, easy to test on the long run, or it's really painful to add bug fixes or retest something after a fix due to side effects and complex structure. Okay, so let's speak a little bit about what are the main tools for quality assurance. I meant that testing alone is not sufficient anymore. But what else we can do? Of course, testing is remaining one of the core tools or enablers for assuring the quality of the software system. So of course, the various levels of testing, like unit testing, integration, performance testing, is a really important tool nowadays as well. However, there are other things we can do to enhance the quality or ensure the quality of the software system with some additional automated user interface testing, for example. But of course, there are tools you can use for static code analysis or dynamic code analysis to automatically detect different kind of problems in the system. You can do some automated checks during the CI/CD integration. And of course, the development process itself has shaped a little bit to integrate more and more activities that can ensure the high quality of the produced product. For example, involving code reviews into the development processes, applying test-driven development, setting up quality gates at the beginning of the development, and consciously and continuously planning some activities to counteract this software erosion effect. So refactoring, increasing the internal maintainability of the system is one really good tool to manage and counteract the effect of the software erosion, this software decay phenomenon. But it cannot be, again, done in large batches as a rare activity. It should be an integral part of the everyday activity of software developers. So a small quality maintaining activity mixed with the daily work, what is proved to work the best in practice. Okay, and allow me to be a little bit biased towards static code analysis. So of course, I don't have time to speak in details of all these different quality assurance activities. You could have guessed that my pick would be static code analysis. Then I would like to speak a little bit about more on how static code analysis can help boosting the quality assurance of systems. So why static code analysis became essential and became one of the cornerstones of software quality assurance processes? Well, it finds issues before execution. So it helps preventing bugs entering the code base rather than detecting them afterwards when the bug is already there. Okay, so it detects security, maintainability, performance, and very different problems very early on, right in the development, right in the build phase of the software product development. It's language and architecture aware, so it can be applied to many different languages. Scales with the code base really easily, so it's practically feasible to run static code analysis on not just on system with 10,000 code lines, but also with millions or tens of millions of code lines. A good example was the Symbian operating system, which was, even in 2001, around 10 million lines of C++ code, which the company founders was able to analyze 25 years back. So it's practically feasible to analyze even the largest code bases. What is more, static analysis does not necessarily require system to be compilable, to be built. In contrast with dynamic analysis, which is really good if you have just code fragments or not even a complete system that doesn't build yet. You have smaller silos of solutions. You can even start testing with static analysis those parts as well, because you don't even need to have a compilable code. It's cheap, fast, doesn't require human efforts. It's basically a tool that runs and provides feedback instantly to the developers. Okay, and there are some type of problems which would be really hard to detect manually. For example, typically memory leaks are the problems which you can only find if you're able to track complex control and data flow throughout the program, which can be easily done by a static analysis tool, but it's much harder for humans and human brain. Okay, again, quite straightforward comparison of what manual testing is good for and what static code analysis is good for. The bottom line here is that they are not interchangeable, so they are not competing techniques, but rather complementary techniques, right? So as I mentioned, static analysis prevents defects. So you try to catch problems in the source code before they become an actual bug in the source code, the repository, while testing validates if the system works correctly according to the requirements, and if there are some bugs in the system, it tried to reveal it. Okay, so they are best if they combine, so they can together provide a better coverage of the quality assurance than the individual techniques on their own. Okay, for manual testing, of course, you need to manually execute some individual test cases, while static code analysis is more like a systematic check of some automated rules defined beforehand. Manual testing is uses the expertise of the humans, so it can serve as an in-depth analysis of the quality of the system, while static code analysis is more like an in-breadth, shallow but in-breadth search of typical problems in the source code. Of course, the magnitude, the number of tests you can execute is very limited for manual testing, but for static code analysis, it can be even tens of thousands of checks easily. The effort required from humans is also substantial for manual testing. Humans need to provide all the inputs and execute all the test cases, while static code analysis, it's basically comes from free. Once you adapt and integrate it into your workflow, it can be run many times. Okay, and typically manual testing focuses on some risky parts of the system that needs deeper look, while static code analysis, as we discussed, increases the coverage remarkably by having this in-breadth way of checking many different rules. Okay, and let me speak a little bit about the core components of SourceMeter, the static code analysis tool our company develops. But basically, it very well resonates with any other static code analysis tools out there. So the main components and the main idea is usually the same. I try to highlight those components, those parts which are a little bit goes beyond any other tools available out there. So what are the main pillars of the SourceMeter tool? It can give you a lot of different measurements or analysis results about the software system. So all you need to have is the source code of your system, and SourceMeter can provide you with source code metrics. Okay, so they are really not new things. Source code metrics have been, the first metrics has been defined some 70 years ago, so they're quite old, like complexity of the system, coupling, cohesion, etc. They are quite well-known concepts that try to measure certain properties of the source code, like how complex it is, how tightly the different parts are coupled together, etc. And they quantify this property of the system. Why this is good? Because if you think about the definition of software quality, it mentions things like understandability, analyzability, modifiability, testability, etc. And these properties basically link directly to these kind of quality properties. So let's take code complexity, for example, which I depicted on the right side of the slide, a very simple coding example here. Complexity basically measures the number of branching statements within a code snippet. Okay, so it's essentially the McCabe cyclomatic complexity is the number of branching statements, conditional statements within the source code plus one. And in this really small code snippet where we have two if statements, of course, the McCabe cyclomatic complexity is 2 + 1, which is 3. The graph representation is the call graph representation of this code snippet, but I will speak a little bit more about this representation in the upcoming slides. It's basically depicting the flow of the control of the statements throughout the program. Each node is a so-called basic block, which contains the sequentially running statements. And whenever there is a branching statement, then of course, depending on the expression in the condition, if it's true, the control goes to one direction, otherwise it goes to other direction. Okay, what does complexity tell us? So the more complex the system is, the more test cases you need to cover all the different parts. So it's immediately connected to the testability quality property defined by the ISO standard. If the complexity is high, understanding the code, finding out where and how to change the code becomes more and more complex. Okay, so by having these numbers, you can get an overall view of some of the quality aspects of the underlying source code. Okay, the code duplication detector is another component that is able to reveal duplicated code snippets. Needless to say, code duplication is something really not wanted in a code base because it scatters and spreads bugs in your code base. So whenever something changes in a code that is duplicated in many places elsewhere, you need to properly propagate your changes throughout all these copies, which often yields to problems. Then there are the so-called coding error detectors, different kind of wording detectors. One subtype is typically the code linters, which are looking for some styling and formatting issues and not that much of a syntactic and semantic level problems in the source code, but more like how to format code, it should be unified, etc., to ease the understanding and readability of the code. And there are some more complex detectors that employ very sophisticated code representations like the abstract semantic graph, the control flow graph, the data flow graph, to perform some deep analysis of the source code to reveal certain complex problems like vulnerabilities, semantic problems, etc. Okay, how source reader works under the hood is basically in a simplified slide looks like this. Without going into too much details, these are the components that I mentioned. Basically, it's starting modulus from the source code and applies a so-called front end. And there is the hint for the name of the company, which is basically a source code parser. That, with the help of this parser, we build a abstract representation of the system itself, from which one can extract these very useful information like duplicated parts within the ASG, calculate some metrics, some coding alerts, and similar. And one interesting component I would like to discuss a little bit more detail is the symbolic execution-based vulnerability analysis and runtime problem detector. So the SourceFilter tool contains a fully custom, own-built symbolic execution engine, which is not common in the static analysis market, which basically tries to simulate all the possible execution paths of the system. So it's something between static analysis and dynamic analysis. It tries to run the code, but so that it doesn't run the code. Okay, it just runs it using symbolic values. And this is really, really useful and really, really good because in that way, we can analyze the potential execution paths throughout the control flow graph. Let me show you an example. So here is a very simple code example here, which tries to verify if the provided 3 points for a valid triangle or not, using the Euclidean distance. And basically, without running this code, one can start symbolically executing the code without knowing what are the P1, P2, and P3 values. Actually, you can build this state graph along the conditions within the program. So you say that, okay, P1, P2, and P3 have some symbolic values, and whenever there is an operation with this value, you note what kind of operation happened to this value. If number 3 got added to this value, then you will have a symbolic value plus 3 as a new value. And at each branching condition, you can collect all the conditions, and basically you try to execute all the different paths throughout the control flow, not just one actual execution will go through one certain path in the control flow. But whenever a branching statement is there, you go in the true branch as well and the false branch as well, but you can apply a constraint on the symbolic variables you track. If you go there, then the symbolic variable must meet the following constraints. You see the constraints in this purple boxes next to this tree. And at each point, you have a certain set of constraints built to the symbolic variables. And whenever you are at this point, you can try solving the satisfiability of this constraint. And whenever this set of constraints are not satisfiable, you know that you reach the point that can never happen in an actual execution because there is no such values for these variables that would satisfy this path throughout the control flow of the program. And you can deduce other useful information by observing these symbolic variables. For example, you can find out if a value of a variable can be potentially null or not. So you can implement a very precise runtime exception detector without having to run the system, right? And this technique will eliminate all the false positives because whenever there is a hit, basically you can print all this trace, the trace of the statements that leads to this particular problem. And you can track back that, okay, if I provide null as value to A in the modified function, then at line 136, A does do something, will definitely throw a null pointer exception. So it's not just a syntactical possibility like static analysis provide, but more like a evidence, because the symbolic execution engine can provide the evidence of triggering a potential problem So with that particular input, this issue is triggered for sure. So this will yield to much more precise results, and you can find much more semantically involved problems in this source code. Of course,
Yeah.
this comes at a price. Yes,
Yeah.
or just
Are you getting to one of the last points?
yes,
or-
yes. Couple of slides, and we are done. Sorry, I speak a little bit too much.
No worries. I like it, but
It's almost finished. Okay, so it comes at the price, as I mentioned, because this state graph that I'm showing you explodes really fast. Of course, you need to apply different kind of limitations and smart ways of collecting data to keep it manageable. Okay, this is just another example that actually comes from an industrial code we analyzed some years back, which reveals again a null value dereference using our symbolic execution. The heart of the problem is the very same as I showed before. Okay, and I'm moving towards the conclusion. Of course, I'm not saying this is a silver bullet. This is a useful technique, but of course, teams face a lot of challenges today. There are abundance of tools. It's not really easy to define what to measure, how to interpret the results. You get a lot of numbers and what to do with this. We see that a common problem is the high rate of false positives of these tools producing, which often yields to a phenomenon called alert fatigue. So developers are tired of going through all these errors, and basically they neglect using these kind of tools altogether. And of course, from the managerial perspective, is another problem is to quantify the economic value of high quality code, because new features have immediate business value, but saying that investing quality will return in the mid or long term is a much less appealing statement. Okay, so what we see works in practice is instead of having perfect accuracy, it's often enough to show good enough results with the proper prioritization and pinpoint some issues that are the most important, providing developer a friendly way of feedback and integration to existing workflows, right? So if developers need to use yet another tool, they often neglect using it altogether. Okay, and what might be the future of static code analysis? Well, I don't know, because I'm not seeing the future, but according to the experience and according to what we see in the industry, we see that with the help of Atmos AI techniques, deeper semantic understanding of the source code becomes more and more feasible. So context-aware findings are things that will become soon the mainstream parts of these tools. They can distinguish different kinds of patterns based on the context, and of course, involving quality early in the software development lifecycle, as I already mentioned this. Okay, and of course, I cannot pass by the fact that the innovation, the research capacity of our company is highly boosted by these European research funds, just like EPTIC. So it helps really increasing international visibility, reach out, but also helps bringing this kind of innovation into life and into integrating into the product itself. Like energy-aware rules that we can check and transform programs to be more code efficient, or implementing automated repair techniques. That is not just the tool is able to detect certain issues, but also automatically generate and suggest some fixes, or built on the symbolic execution engine, implement some very sophisticated vulnerability detection. Okay, and of course, lowering the number of false positives is again another major thing we could reach in another EU project. Okay, and finally, what can the organization do to prepare for the future? It's basically what I don't think will change is that humans won't get out of the loop for a while. Human judgment will remain really critical. Testing creativity in quality assurance will be irreplaceable. Tools will support decisions, but won't replace engineers. So investing in early quality checks, balancing automation with humans, and focusing on meaningful metrics is basically the best approach a company can take. Okay, and to summarize all this that I was talking about, the key takeaways before our discussion session is that, as we discussed, quality has shifted left, so quality assurance processes starting early in the life cycle, and the trend is to be as lightweight as possible, so smarter, simpler checks early in the development life cycle. Prevention is always better than detection. Fixing issues during development is really cheap. Meanwhile, fixing in operation is 10 or even 100 times costlier. And the combination of static analysis with different kinds of testing techniques provides a stronger system, a better coverage for quality assurance. And the future of quality assurance, I think, will be continuous QA is integrated, the full software development lifecycle, and of course, this advent of AI agents that are basically start using by the developer community already will be integrated with these QA activities to make it more efficient. But as I see now, humans will remain in this loop for quite a while to ensure proper quality of products. Okay, thank you very much. That would be my talk. So if anyone has any feedback or questions, I'm really happy to discuss it.
Thank you very much, Peter, for this great talk. We have only a few minutes left, and obviously I do have some questions, but I would like to give the floor to the colleagues if they want to ask a question or raise their hands. There's a small group, so if you want to talk, I can give you the floor. And at least, and to a certain extent, you already mentioned it. But at least one of my questions would be, now in this age of AI supporting software development, which can oversee so many more issues than what a human can oversee, why can't the AI create software without bugs or without code issues?
I don't think so. So as we see it, the AI-generated code is basically nothing better or worse than humans do. So a lot of studies report, and we ourselves experience, that AI-generated code can as well contain quality and security problems as well. So it's not true that, okay, we generate everything by AI and AI is flawless. It's far from it. So if you can use AI in a careful way, with an iterative approach, taking special care to quality and security, then the outcome will be good, high quality, and free from security issues. But if you just use it as is, it often produces vulnerable code. It often produces non-perfect code, code with performance problems. So I think just by using AI tools for generating code won't yield to better quality as is. So as now, you need to invest some special effort to maintain the quality, even in that case.
Maybe a stupid question. Because if I'm using the AI for creating content, and I always give it some feedback, so like, hey, I like this, but is it also possible to say like, create this and do a static code analysis? And does Cloud or
It can.
just-
I mean,
do they understand it?
it's possible. So you can do two things. You can use these AIs and you can instruct it to reconsider generating new solution, taking into consideration this quality concern or security concern. But then you, as an expert, you need to be able to assess the quality of the security of the generated code. Or the other thing that you mentioned, it's also possible to run some external static analysis tools with these AI agents. So AI agents can employ external tools to produce their output. So it's fairly possible to create an agent that will generate the code, but before it gives you back, it calls out for third-party external static analysis tools, runs the analysis, gets back the results, and based on the results, refines the answer it will give to you, and you get back a final answer that eliminates all or the most important warnings. So it's totally feasible. It's not stupid. It can really work.
Any other questions by colleagues? Oh, my last question, this, like how you presented, this is really professional software development business. If you want to, let's say, tick all the boxes and take all the approaches. In the end, AppTake also has as a target audience the SMEs, the smaller companies who are developing, let's say, smaller platforms. What would be your recommendation where to start?
Where to start? You mean?
So which measures should we definitely take?
Okay, I see. I see your point. Well, what I would do, yeah, it's not a simple question to answer. There are so many different measures, but there are certain metrics. So I would go for 2-3 critical source code metrics. I would observe, like complexity, for example, one example, and coupling, and the clone ratio, the duplication ratio. So I think these three would be a very good first set of indicators to watch. And additionally, these advanced symbolic execution or deep code analysis based high severity warnings. So these tools provide prioritization to the findings. And I would go for the highest prioritized issues. These are typically the ones that needs immediate attention. So small companies with limited resources can start by watching these measures and trying to optimize or improve these measures. So what typically works in practice is not to invest a lot of effort and fix everything, but rather start and put in a small but continuous effort and start changing the trend so that in the midterm you can have some impact. So I think that's a strategy that worked for quite many companies, customers we have.
Thank you very much. That sounds like a plan. Especially also for reasons of time, because I think we can talk for quite some time more. But I would like to work towards a conclusion, so make some closing remarks. But first of all, mainly, Peter, really thanks a lot. I very much appreciated it, and I see colleagues that have to leave because of time, but not because of lack of interest. So thanks everybody for participating and joining the new series of AppTech Dialogues. One thing to keep in mind for all of us, we have an upcoming hackathon scheduled in June, so that will be good fun to participate. And the next AppTech Dialogue is scheduled for Monday, the 23rd of February, where we want to talk about zero trust and application security, and do that especially along the line of the partners that we do have in the AppTech project, in order to also give them a floor. And we have a few great speakers in mind, but they need to be confirmed. Any other input is always welcome. Again, I think on behalf of everybody, Peter, thanks a lot. Wishing everybody a great afternoon, good evening, and hope to see you soon.
Thanks a lot.
Bye-bye.
Thank you. Bye-bye.
Great job.
Thanks.
I liked
That's
it.
a bit longer than expected.
That's how it often goes. But,
Yes.
okay.
Okay.
Again, thanks a lot.
Thank you for organizing. It was very smooth and flawless. Thanks a lot.
Yes, great. See you next week.
See you. Bye-bye.
All right. Hey. Is it a